Sure, that sounds good.
Go ahead.
Cool, welcome everyone. It's my great pleasure to introduce Manuel Egele, who's been with us for a couple of months now. I hope that many of you already had the opportunity to come and talk to him. But if you didn't have that opportunity yet, he's going to be around for the spring semester as well. And we do hope that we can actually see each other in person. He'll be around for coffee, so come join us. Manuel is working on security, broadly on system security, and has been exploring a lot of different fun projects in the past, from like core system security projects that go down deep to the hardware on embedded systems, low-level architectural details, but also up on the stack, up into securing the clouds and webs. He's come from, he's visiting us from Boston University, where he's an associate professor since, I think, also this year, summer this year. And before that, he was in the ISAC lab at UC Santa Barbara, and comes originally from Austria to us. And yeah, he's been working and dibbling in security for many, many years. And I think it's going to be nice to see a little bit of a medley and focused talk by him on what he's actually targeting. I don't want to spoil too much. I'm actually very excited to hear this talk. So I want to hand it over to you, Manuel, and you can go ahead and blow the people away. So please do that.
Thanks, Matthias, for the introduction. Yeah, I'm very happy to be here. Can pretty much spare the brief introduction then, since Matthias did that. Yeah, as you can see from the camera, this is how I usually look. If you encounter me at EPFL nowadays, this is more like it. So Matthias briefly sketched about the topics that I've been working on. So the things that I really like doing are applying program analysis techniques to security problems in all sorts of domains: Internet of Things, mobile, cloud. We've dabbled in architectural enhancement for security, also worked on web security. And for those of you who joined the security and privacy seminar yesterday, I've been talking a little bit about my web security aspects, specifically when it comes to cookies. But for today, I have something different planned. And so I'm going to be talking about the cloud security and the security of web applications for the remainder of this seminar. If you happen to have questions at any time, please don't be shy, just jump in and ask. I'm more than happy to keep this as interactive as possible. All right, so this talk is about bugs, right? And if you have read any security news over the last week, you obviously came across a log4shell, a bug in the log4j logging library in Java. There is also shell shock, a little bit older. And one thing that we can say for the newer vulnerabilities is that the older ones had better graphic designers, that's for sure. Other bugs that come with their names are, for example, Venom, which was a vulnerability in a floppy controller for cloud deployments, and then also Drupal-Geddon, which is a vulnerability for web applications. And so the latter two I put in here because they're excellent references for what we're going to be covering throughout this talk. All right. So bugs, specifically software bugs. And as Buzz Lightyear so eloquently said at one point, they're really everywhere, right? Any piece of software that we write, pretty much any piece of software that we write has at least some bugs. So we probably need some strategies on how to deal with them bugs. The first strategy would be to try to detect bugs pre-deployment. And so here, technologies and mechanisms such as testing, verification, or fuzzing as an application of testing come to mind. So really trying to identify bugs and hopefully fix them before we actually deploy the software into the world. That's one approach. Another approach could be we could try to mitigate the effects that bugs might have. So for example, we could make our piece with the knowledge that whatever software we ship, irrespective of how much testing we do, there will be bugs in there. Nonetheless, we can still strive to minimize the negative consequences that exploits might have if attackers actually misuse those bugs for their nefarious purposes. And here, various security principles come to mind that can be brought to bear here. And one of the examples that we'll be looking at is the principle of least privilege. Now, there might be other mechanisms or strategies to deal with bugs. Another one that I came across might be magic amulets. I don't know how effective those are. And maybe there are some others that I didn't include on this slide here. All right, so but how does the rest of this talk look like? Well, we'll take these two orthogonal approaches of detecting bugs pre-deployment and mitigating exploits post-deployment and wrap them up in a nice talk, hopefully. So for our pre-deployment bug detection approach, I'll talk about Morphuzz, which is a system that automatically finds bugs in virtual machine hypervisors, or specifically the virtual devices that comprise these hypervisors. The goal here is to find bugs and get them fixed before the software is shipped. So in terms of exploit mitigation, we'll look at a system that we recently released called Saphire. And the Saphire retrofits the principle of least privilege for PHP web applications. That has the advantage that even if there are bugs in your PHP web application and an attacker has an exploit for this bug, the attacker's capabilities and exploits are limited to the privileges that the corresponding script needs, and therefore taking away a lot of the liberties and power that attackers have when compromising web applications written in PHP. All right, so let's dive right into it. Morphuzz is our system to identify bugs and vulnerabilities in virtual devices. So this is a paper that has been accepted for publication at Usenix Security 2022. So you're among the first to hear a talk, actually a presentation about this system. All right, before we dive into the details of virtual devices themselves, let's just look at how device input-output, or I/O, happens on computers and why this is necessary. Well, as a first observation, a computer that does not have any I/O, does not accept any input, does not produce any output, is obviously of very limited use. And therefore, I/O is crucial to make use of our computing resources. And a couple of examples for I/O is, for example, when you press a key on your keyboard, there will be I/O activity. If you, for example, store the LaTeX source code of your most recent paper on disk, that also produces I/O activity. If you then go and sync your Git repository over the network, again, triggering I/O activity. And if those examples don't speak to you, maybe one of the many devices that are listed here below are something that you can identify with. All right, so how does this I/O actually work? Well, for starters, let's look at X86, the architecture that most of our computers run on, unless you run a very recent ARM M1 Mac. All right, so in X86, we have three different types of I/O. There's port mapped I/O, which basically is a separate address space that allows the CPU to communicate up to word width values with I/O devices. And so for that, there is specific instructions, specifically in and out, that allow the CPU to do that. While this is very important for the project, in this talk, I will not spend any more time talking about port mapped I/O than it is on this slide. What we will encounter throughout this talk is memory mapped I/O. And so in memory mapped I/O is basically a situation where device registers are mapped into the physical address space of your computer. And then the CPU can interact with those device registers simply by reading and writing to those addresses that are backed or mapped to device registers. Again, these reads and writes are going to be a maximum word width. All right, so that's nice if you have a couple of bytes to send around, but if you want to make larger transfers, then usually we're dealing with an I/O mechanism called direct memory access, or DMA. What DMA does, it's using either PIO or MMIO to tell the device where in physical memory it should either retrieve or store how much data. And then the rest is taken over by the device itself, which has direct access to the memory bus and can then read or write information there. This has the advantage that the CPU, while the device is doing input-output, the CPU can go and do other useful computation instead. All right. So much for the words. Let's look at some pictures. So let's go through a simple example for memory mapped I/O. We start out with, we have our CPU here and we have our physical memory, the RAM. And then someone might want to plug, for example, a mouse into the system. So how does the information that the mouse moved get to the CPU and subsequently to the program to move the cursor around? Well, the mouse needs to be plugged into a port on your computer, and then there's usually an I/O controller associated with that port. So that's this little chip down here. You can tell that the controller is much less powerful than the CPU because it has much fewer VIOs. And so when you move the mouse, what's going to happen is that the controller will write into control registers and data registers. So if you move the mouse, the controller will first write information about the movement that happened into the data register. It will then set bits in the configuration register, which the CPU can check. And if the CPU checks that the configuration register basically indicates that there is additional information to read, the CPU can go look at the data register and read the information from there. Ta-da! Now the CPU knows that the mouse was moved and by how much, which direction, and so on and so forth. So that's great if you have, as I said, very limited rates of data information. So let's look at an example of DMA, direct memory access. And in this example, let's actually look at a network interface card. So basically the scenario that we want to look at here is the CPU has some data that it wants to send out of the machine through a network interface card. So let's bring in a network interface card here. So how does this work? Well, we now have a data region in memory that is much larger than the data register that we've seen before. In fact, the size of this data region is entirely determined by the operating system. Furthermore, we have a control register, control information that has a little bit more information than we had before, specifically how many bytes or how big the data region is and the address of that data region in memory. And so what the CPU then does, it basically writes the information about the Ethernet frame that should be transmitted somewhere into memory. Then basically sets the configuration register to say how big the data region is and where in memory that data region resides. And then the CPU simply tells the network card, please network card, go and send the frame that I put in memory. What happens next is entirely controlled by the network interface card. So the network interface card will read from the configuration information where the data is stored and how much data it should read from memory. It will use that information to read, process, and send that data over the wire. So what does the process involve here? Well, it turns out that modern devices can have fairly complex logic embedded. One example, for example, would be CRC offloading that network hardware can do. Not particularly complex, but serves as an example nonetheless. The wobbling animation that you've seen on the data buffer up there before was basically to indicate that between two DMA transactions, this buffer can move in memory wherever the operating system desires. So that is as opposed to the memory mapped IO situation that we had before, where the configuration and data registers are hardwired to physical addresses and they won't change as long as the system is running in that configuration, right? Interacting with DMA is much more variable, so to speak. All right, so now we know how the CPU can basically make sure that network data is being sent out of the system. So looking at a very simplified computing stack, the things that we've been talking about here is, for example, a network interface card down here, and then you can plug your mouse in, probably more realistically through USB, what you get nowadays. But on top of the hardware, you usually have an operating system and then applications that run on top of that operating system. That's no surprise to anyone here. But we're not looking at real systems. What we really do, or what we are interested in, is looking at virtualized systems. So if you have one of these instances that we've drawn on the previous slide, what we can do is we can simply do as computer science always does and introduce another layer of abstraction. This abstraction is called the hypervisor. And so now on the real hardware, there is the hypervisor running, and all these little hardwares that we have here basically all morph into what is called virtual devices. So now the individual operating systems, or the so-called guest kernels, no longer directly interact with the real hardware, but they interact with virtual hardware instead. And so this is how you get a server that runs potentially multiple virtual machines. Each of these silos here is a virtual machine. And if you're a cloud provider, these can belong to different tenants, right? And so as a cloud provider, there is a number of threat models that you probably have in mind. And one thing that you definitely want to avoid is that a tenant can break out of their virtual machine and potentially peek into or muck around in virtual machines that happen to be co-located on the same physical hardware. So if you have a tenant who runs malicious applications or who got compromised, they might be able to compromise the guest operating system and the guest kernel. If they further manage to breach the separation boundary induced by the virtual devices and reach into the hypervisor, then potentially they have the capability to do all of these nefarious things that I just mentioned. Read secrets from other virtual machines, poke around in virtual machines. So definitely something that we do that as a cloud provider, you probably want to avoid. All right. So previously we've seen how the CPU can send data over a real network interface card. Well, what if that network interface card is not real, but rather a virtual device? Well, again, we have our CPU, we have our physical memory, and we have our network card. And so we could go through the entire spiel again, but then you would end up with exactly the same figure as we've seen before, with the only caveat being everything's exactly the same, but the device itself, instead of being hardware, is now completely implemented in software. And as we've seen at the very beginning of the talk, every piece of software has bugs. All right. So why am I so confident in saying this? Well, we have plenty of evidence that bugs exist also in virtual devices. So there have been news reports on VM escapes, so exactly the type of attack that I described in my previous slide, where a tenant can break out of their virtual machine and compromise the hypervisor. For example, in qemu, which is one of the most popular open source hypervisors out there, if you look for CVEs, there are plenty CVEs that affect all sorts of virtual devices in pretty much any hypervisor that you can think of. Again, these bugs can then affect various hypervisors from different manufacturers. So it's not just limited to qemu or any specific hypervisor. And this basically brings us to the classic hypervisor exit or a VM exit vulnerability, Venom, which was a fairly impactful vulnerability. I believe it was reported in 2015, so it's fairly old already. But basically what was at fault here was that the implementation of the floppy disk controller, the virtual device floppy disk controller, had an out-of-bounds buffer write vulnerability that allowed the attacker to basically break out of the virtual machine and compromise the hypervisor. This was a problem because a lot of virtual machines back then, and probably still are, by default configured with a floppy controller. Beats me why that is the case in 2020. Nonetheless, virtual machines with floppy disk controllers are definitely still around. All right. So the virtual devices themselves are basically the abstraction boundary and security boundary between what is usually attacker controlled, at least in a cloud deployment, and what is operator controlled, namely the hypervisor. All right, so now that we understand how device I/O works and how that translates to virtual device I/O, what we really wanted to do with the Morphuzz project is, based on the knowledge that bugs exist in virtual device implementations, we want to find these bugs before the software is being released. We want to report these bugs, and then we want to fix these bugs. Almost true. What we really want is those bugs to get fixed. So we're really not hot on going and fixing the bugs ourselves. Nonetheless, what we want to do is to make it as easy as possible for the developers of the virtual devices to get those bugs fixed. And so I will have a dedicated section in the presentation that talks about our efforts to make this as easy as possible. All right, so here we have the overview figure of what Morphuzz does. It basically operates in 3 steps. In the first step, we have to prepare the hypervisor. So there's a little bit of manual work involved for each hypervisor that we're targeting. In the second step, we basically execute a fuzzing campaign to find bugs and potential vulnerabilities in the virtual devices implemented by the hypervisor. Finally, we go through a step of that we call unbending, a crashing input. So whenever we find an input that crashes the virtual machine, we have to, quote unquote, unbend that crashing input. And finally, we have to report the crash. So the important aspect here is that Morphuzz will hook into all MMIO accesses. So whenever a device or whenever the CPU is communicating with the device through this memory mapped registers, Morphuzz will be involved here. And similarly, Morphuzz will be involved whenever the device is using DMA to read from or write into memory, right? As a fuzzer has to provide random input or quote unquote, a random input to the things that are being tested. If you're testing virtual devices communicate with device IO, as we've seen on the previous slides, through port IO, memory mapped IO, and DMA. And that's exactly what Morphuzz intercepts, and then has the capability to introduce or provide randomized data. And then, as I mentioned before, I'll talk a little bit more about reporting the crash, as this is something that is slightly out of the ordinary in terms of technical research presentations. All right, as I briefly mentioned, Morphuzz is relying on a fuzzer. And so we didn't come up with a new fuzzer ourselves. Instead, what we did is we leveraged libfuzzer, which is a fuzzing engine that ships with the LLVM compiler toolchain. It leverages code instrumentation at compile time. And then libfuzzer lives as a library in the process that is being fuzzed. In our case, that is either qemu or the other hypervisors that we fuzz. Importantly, libfuzzer itself does not provide state resetting. And so what we had to do is basically come up with what's called a fork server model. So that is known from other fuzzers already, where basically before trying a new input, the fuzzer will simply fork the qemu process, which means that every process starts with a clean state. And that is very beneficial if you want inputs that you can reproduce or to use to reproducibly induce crashes. And so one important aspect within Morphuzz is an interpreter that we created. And the interpreter basically turns random inputs into sequences of IO, into sequences of this input output. So you can see this illustrated on the right side here. So we have random input coming from the fuzzer. And this magic box here is basically our interpreter that turns those bits into input-output sequences that you can see basically on those instructions that are listed just under the box here. And this includes, for example, port IO, as we can see through this out-L function, or simply memory mapped IO, which we get through all the writes here. And it turns out that Morphuzz is really successful in finding bugs that are deeply nested within the implementations of those virtual device implementations. As you can see here, we have an illustration of a bug that Morphuzz found. And so we can actually see that not only does Morphuzz have to set up the PCI controller first to basically set up two memory ranges for the XHCI USB controller, but there is also this section of transfer rings that are basically nested DMA structures that have to be set up, quote unquote, correctly to even trigger or reach the buggy line of code in the implementation of the USB controller. Matthias, do you have a question?
Yes, I actually wondered regarding your magic interpreter, how is this different from a custom mutator written in libfuzzer? This sounds pretty much like your LLVM libfuzzer custom mutator implementation. So I wonder what's special there, or if there's any magic sauce that I'm missing.
There is very little magic sauce. That's why I'm not talking about it in detail in this presentation. All the details that you need to know are in the paper. Maybe just to answer the question, what the interpreter does is simpler even than the mutator in libfuzzer. So it simply takes whatever the bit stream is that comes in, takes the first, I don't know how many bits as a modulus to indicate which instruction to execute, and then takes the remainder of those bits as operands for the instruction. So it doesn't even try to combine or mutate anything. It simply just consumes and translates it.
Right, makes sense. But the translation is actually magic that's happening. So you're,
Yes.
Okay, cool. Thank you.
But it's very simple. It fits on less than one page in the paper. All right. So then we run this entire shebang and perform an evaluation. I don't expect you to read this table here. I have a couple of highlights that I want to call out. So we tested it on 2 hypervisors, on qemu and Beehive. We tested it on 33 virtual devices, which to the best of my knowledge is the biggest evaluation in the space of fuzzing virtual devices so far. We reached about 81% code coverage on average over those devices within 24 hours. We identified during our evaluation for the paper 71 bugs that we reported, and as we will see later on, post-acceptance of the paper, there are many, many more bugs that were also found and get reported. Maybe one thing to also call out here in this table is that we thoroughly evaluated our implementation against the 3 state-of-the-art systems that already existed for virtual device fuzzing, which all have their benefits and limitations. The biggest limitation is that up until that point, really no one could deal with nested DMA communications, which was, for example, necessary to find the bug that I mentioned before. All right. One thing that I mentioned before is that we are not interested to fix all the bugs, right? The reason being, realistically, we are not well equipped to do that. So during this project, we closely collaborated with engineers at Red Hat, and those engineers are some of the main developers and maintainers of various systems and subsystems within qemu. And one of the bugs that our fuzzer reported required the Red Hat maintainer to do work for 2 weeks. So it didn't just take him 2 weeks to get back to us. He actually was working on it for 2 weeks to significantly restructure the PCI subsystem within qemu to address the bug there. So it would not be reasonable for us to try to identify or to understand how the PCI subsystem works, and others are just much better equipped to do that. Because ideally the maintainer already has all the background knowledge and therefore is faster in fixing the bug. Nonetheless, we want to do whatever we can to make the developer's job easier. Because one thing that we also heard from our interactions with the developers early on is that people who just basically throw bug reports over the fence, oh, our fuzzer found this bug, we'll look at it, very frequently are dealt with just deafening silence because there's not enough information, there is a lot to reproduce the bug, there is a lot of mental burden for the developer to understand what the fuzzer does. And so these are some of the things that we wanted to sidestep with Morphuzz in order to turn this into something that, in addition to, in my opinion, a pretty cool research paper, makes also some practical impact and be of lasting value. And furthermore, as opposed to many other fuzzers, Morphuzz inputs are interactions with virtual devices and not just simple command line arguments. So reproducing a bug could become significantly more challenging than with regular standalone programs, so to speak. So yeah, what we wanted to do is to make the developer's life as easy as possible. And that's why we came up with simple and independent reproducers. And so that's basically what the unbending, the step 3 in Morphuzz is accomplishing. So Morphuzz uses the qtest framework, that's the testing framework that's built into qemu, to turn fuzzing inputs into standalone reproducers. And this means that those reproducers can be run with an unmodified qemu to confirm and reproduce the bug. This is of great advantage for the developers because they don't have to build qemu with a fuzzing configuration just to reproduce the bug and then try to translate this into an unmodified qemu version. Our reproducers, you just pipe them into qemu, and then the developers can try to figure out what the bug is. All right, the inputs are minimized and they nicely fit into commit messages. So this, for example, is one of the commit messages that was generated as fixing a bug that was detected by Morphuzz. And so if you look closely, this here is all that you need. You copy paste this into your command line. And if you run an unpatched qemu version, then qemu will crash, right? Really straightforward to reproduce the buggy behavior in an unmodified qemu version, allowing developers to quickly get at where the bug is and hopefully to fix the underlying issue. All right, so beyond reproducing the bugs themselves, what we also did is, because this is a recent Usenix paper, we participated in Usenix artifact evaluation. And pass that artifact evaluation. That's great, looks nice on the paper. Nonetheless, what we also did is that we upstreamed our fuzzer into qemu. So if you check out qemu, a new qemu branch on the, I believe they still call it master, maybe it's the main branch, the fuzzer is there. Furthermore, it's integrated with Google's OSS fuzz. So Google is basically providing lots of CPU resources to fuzz virtual device implementation within qemu for the community, basically. Plus, there is documentation on how to use the entire shebang that is also upstream in the qemu, in the official qemu documentation. So if you want to use and experiment with Morphuzz, feel free to just check out the latest master version of qemu, follow the documentation, and get started there. All right, now that we made our cloud secure, let's change gears a bit. I like my bike, so I had to feature that in my presentation. All right, so we talked about how to detect bugs pre-deployment. Let's quickly switch gears to mitigate exploit effects, so post-deployment mitigations. And so here we'll talk about the system that we call Saphire, which is doing sandboxing for PHP applications with tailored system call allow lists. Why are we looking at PHP? Well, turns out that if you scour the web, you'll quickly figure out that about 80% of all reachable websites are powered by PHP. And so frequently these are systems such as WordPress, Drupal, MediaWiki, and so on and so forth. And if you only look at the most popular of those, WordPress alone has a market share of 40% of all reachable websites. And so specifically what we're interested in is remote code execution vulnerabilities. Because these basically allow an attacker to execute code of their choosing on the attacked platform. And so remote code execution was and continues to be really popular. And if, as an attacker, you find a remote code execution vulnerability, you immediately have hundreds of thousands of targets if those vulnerabilities are in CMSs or content management systems. And even the exploit dealers will give you significant money if you report some of those RCE exploits to them. All right, at the core of Saphire lies the principle of least privilege. So that's postulated by Salzer almost 50 years ago by now, which basically says that every program should operate using the least amount of privilege necessary to complete the job. All right, so this principle of least privilege is basically non-existent for PHP or pretty much any other web applications. That is, all scripts of a web application have to run with the same ambient authority, and process-based defenses usually only apply to the interpreter process, irrespective of which script is running, hence the ambient authority. However, meaningful programs and remote code execution attacks themselves interact with the OS, with the operating system, through system calls. So how do we apply the privileges of least privilege here, the principle of least privilege here? Well, in the context of our work, a program is an individual PHP script, and the privilege is simply the availability of a given system call. So obviously, we are not the first ones to try to restrict system calls. So system call level mitigations have gained widespread adoption. On Linux, you would deal with seccomp. And so a lot of popular software, including qemu that we talked about before, but also the Chromium browser, Firefox, and so on, make use of seccomp to basically narrow the attack surface. A similar facility would be Pledge on OpenBSD. And in OpenBSD, there is roughly 70% of the packages that actually make use of this facility. However, applying system call filters to PHP scripts is non-trivial because we cannot filter system calls only by looking at the scripts. And we can also not apply filter system calls by only looking at the interpreter. Instead, we need to look at both of these components in tandem. A simple example is listed here. So if you have a native program on the right-hand side here that makes a system call, say an open system call, then what you will see is there is a direct transition into the kernel space down here, and the system call will be invoked, whatever that system call is. However, if you do, for example, fopen in PHP, then you can have really interesting behavior because intuition and experience with libc would dictate that, well, fopen, you can open files, and therefore you might see an open system call. But this is not just libc, there is the PHP interpreter in the way. And so if you do fopen, you can actually pass a URL, at which point the fopen API call within the PHP interpreter will automatically dispatch to the socket API and fetch remote content, right? So translating whatever the API functions within PHP, which system calls they relate to, requires an understanding of what the PHP internally does with those API calls. All right, and so if you look at our Saphire system, it consists of 3 stages. The first stage is a mostly static analysis over the PHP interpreter itself. It produces a mapping from the API functions that PHP exposes to PHP scripts to the underlying system calls. So which API function can invoke which system calls. The second part analyzes a given PHP application. And so there, the system figures out a mapping between each script that comprises the application and the API calls that are being invoked by this script. And the final step, in the third step, what Saphire does, it's basically combining these 2 mappings and therefore can relate a given script to the system calls that it potentially invokes, and then configure the execution environment, in our case with seccomp, to make sure that the current PHP process that is executing that script can only invoke those system calls. All right, I have here a couple of detailed slides, but in the interest of time, I'll skip through those. So they basically just explain how these analyses happen. So what we did after we built the system is we evaluated it with 6 popular PHP web applications. We also used 9 known vulnerable plugins for WordPress specifically. So in total, we had 22 vulnerabilities where we had proof of concept exploits for them as well. And so this is the analysis result that we see for WordPress 4.6, for example. It requires a little bit of explanation how to read this graph. So on average, Saphire filters out 80% of dangerous system calls. So there's a little asterisk here. What we mean by dangerous, there is no formal or official definition. We simply relied on what Benashi et al. Declared in 2002 as being dangerous system calls. And so that list basically distinguishes a non-dangerous from a dangerous system call. More than happy to debate this after the talk. So if you look at our results here, on the y-axis, we can see the number of system calls. So this was run on Linux kernel 4. I don't remember exactly what, where you have 330 system calls in total. On the x-axis, we have the scripts. And so basically every tick on the x-axis is 1 script within WordPress 4.6. And so as you can see, WordPress consists of roughly 1,500 different scripts. And now we can see for each script, the number of available dangerous system calls. So that's the thin red line on the bottom, dark red line on the bottom that you hopefully can see if you squint. The orange area, the orange shaded area on top of that is the number of system calls that are available to the script, but are not considered dangerous. And everything that's above that line or above that area will be blocked. And so that consists of the deny listed system calls that are not dangerous, plus the significantly larger area, dark red area, of deny listed system calls that are considered dangerous. And so these are basically the results that we have for WordPress 4.6. We have the same for the other applications that we tested as well. The graphs look fairly similar in the sense that there is this shelf behavior there, and the number of available dangerous system calls is really small for most of the files, or even non-existent for most of the scripts. So if you look at our evaluation, at our security evaluation with real-world exploits, as you can see here, we have them listed from Drupal over Joomla all the way till WordPress. And very importantly, what we can see on the rightmost column over here, these are basically the system calls, the dangerous system calls that are still available to an attacker who can exploit the vulnerability that is there, right? In this work, we don't try to fix bugs. We're trying to minimize the impact of exploited bugs. And the impact that adversaries can have with malicious system calls are very small at this point. All right. Moving on to the performance evaluation. Well, for performance, there's only a few things that we have to say. The first stage of PHP only runs once per PHP version. And so since PHP versions are released fairly infrequently, This can be in the order of years that you have to run it again. It takes 1.5 hours, but very infrequently, so not particularly relevant. The second stage runs once per web application version. So there's more updates there, but nonetheless, it can still be months between different updates. And that analysis takes for WordPress, for example, only 5 minutes. What is really performance sensitive is the third stage, because the third stage executes once per request in PHP. So you have to do it multiple times per second on a busy web server. And fortunately, our impact there is somewhere around 2 milliseconds in a real world deployment. And so that's what you have listed here. So we basically look at WordPress configured with Nginx with various levels of concurrent client threads. And we can see that the overhead that we get is very small in percentage terms. And if you look at the millisecond values here, they're very small as well, right? We have 2 milliseconds here. Yeah, very small performance overheads. We also evaluated that with Apache in addition to Nginx, so it's broadly applicable. So what we did with Saphire is that we showed that the system call filtering mechanisms that are really popular for regular software is applicable and effective also for script-based applications, even in a performance critical environment such as web applications. Saphire itself, it's fully automated. It protects real web applications against real-world exploits. It has very few false positives, even when configured in the most restrictive configuration. It's built on mature filtering primitives, specifically seccomp for Linux, and incurs relatively low overhead. It's open source, and again, as a Usenix paper, passed the artifact evaluation, so you can access it, look at that as well. So, in summary, I didn't get time to cover the magic amulets, but I'm just postulating that we don't have them right now. And so in the absence of those magic amulets, we can either try to detect and prevent bugs and do that pre-distribution, or we can try to mitigate the exploit impact, and that's what's happening post-distribution. We talked about 2 systems, one in each of those 2 categories, Morphuzz to detect bugs in virtual device implementations, which allows us to improve the security of our cloud and your cloud. And we looked at Saphire to retrofit the principle of least privilege to PHP scripts, which makes web applications as a whole more secure as well. And let me reiterate that all of our stuff is open source. In the case of Morphuzz, it's even upstream into qemu. It's continuously fuzzing via Google's OSS fuzz, continuously reporting bugs. It reported more than 100 bugs by now. All of it is automatically integrated into the qemu reporting environment. Yeah, the code is there. The artifacts were evaluated, meaning that some student was able to use our artifacts and produce at least some results. And with that said, I think that's everything I had. Looks to me right on time, open for any questions that you might have.
Cool. Thank you very much for the presentation, Manuel. Questions? Keep them either by, ask them either by raising your hand, and I will pass the mic to you folks, or write them in the chat. To get people started, Jiang had a question and he wondered why PHP for Saphire?
Why PHP for Saphire? I mean, really, any scripting language would have worked well, right? For regular standalone application, seccomp and variants are prolifically used, so there's no reason to do it there. Nonetheless, like if you do seccomp on the PHP interpreter, you get a problem because all the scripts run then with the same permissions. And so you can either make it as permissive as possible, or you're breaking scripts if they need that functionality, right? And so we needed to pick a scripting environment to apply the technology and methodology here. And PHP seemed to be a logical choice, as I tried to argue in my presentation. It's really popular on the web.
Right. As a follow-up, one of the questions I had was that in the couple of figures you showed for Saphire, it seems that like 80% of the logged system calls are shared among all the scripts you looked at.
Ooh, that's actually a deception. Good observation, but you mean this big yellow box here, or like the big area that's orange here?
One yellow is not the same yellow.
Exactly. The yellows between different columns vary. And also the red ones between the different columns here vary as well. So this is really just treating all system calls the same, with the only difference being, is it a dangerous system call or not?
Right.
So there is no order in the column.
So I wondered how much is the overlap that you could just like do as a generic filter compared to these fine-grained filters?
That is a very good question, but now I painted all over here. If you look at the right tails of the figures, for example, over here, you're pretty much at 0 dangerous system calls. But you cannot block them everywhere, because here at the beginning, you're clearly not at 0, right?
But the dangerous one are like open at and such.
Yeah, the thing that we're really most interested in are execve, because if you can do execve, then you can do really nasty stuff.
Yeah.
Right.
But
So open and specifically, if you look at this, for example, right, you can still do unlink as the adversary. And then one of the comments that we got in the reviews were, yeah, sure, but then I can go and kind of delete important stuff on the web server. So this is only the system calls that can be made, or they can be issued by the interpreter. The protections from the operating system still come into play. So while you can issue an unlinked system call against a file you don't have write permissions to, the operating system kernel will tell you nicely, sorry, you can do that. And the same thing applies here as well. So yes, you can issue an unlinked system call, but it can only be successful against files where the web server has write access to already. And so a sanely configured web server will only have very few resources, directories, and files where it actually can invoke a successful unlink system call. So
maybe a more abstract question. There's a couple more in the chat, but I'm abusing my time as the host here to ask those questions. Could I compare this, or I would like to hear your opinion on comparing this to Android and Android applications. Now, let me say a sentence to that and what I mean by that. On Android, each app runs as its own user and therefore is constrained to their own directory. So if you would run each whatever instance of a PHP app as their own user, how would this relate to your system here? Would this be better? Would this be easier? Would this be simpler? Would this be harder?
So it depends on your definition of what a PHP app is. If you run the entire web application as its own user, right, consisting of 1,500 files in the WordPress case, then you don't gain anything whatsoever over the current installation, right? Because it's simply—
Wait a second. You're not doing this on a WordPress basis, but on each script individual. Oh, I didn't get that.
Exactly. Yes, that's the important part, right? If you did it on a WordPress basis, you would only have one set of system calls that you have to either enable or disable for the entire WordPress. The important thing about Saphire is that it creates a system call profile for each individual script, including includes and resolving class autoloaders and all the nasty program analysis that you have to do for PHP to get the correct list of system calls or set of system calls that should be allowed for the corresponding script.
Right. And in that case, the attacker will have to go for the most privileged script, which is hopefully the most reviewed. And you could actually highlight that. Okay, exactly. Cool. I see. That's actually kind of neat. Cool. Question, can Saphire work on other interpreters? What about Python?
So Saphire itself, the technique underlying it will apply to other script or to other interpreters equally well, right? The question at hand, or the tasks at hand that one would have to do this for Python is basically write the program analysis for the Python interpreter. So there might be, if you look at the overview. So we have two parts of program analysis. In the first part here, and in the second part over here. And so the first part of the program analysis is basically a source analysis on the PHP interpreter. And so if our analysis passes run on the Python interpreter just fine, then potentially you can reuse quite a bit of that analysis. The second part of the analysis, of the program analysis, is a source-based analysis on PHP applications. And that obviously you would have to completely redo if you want to apply that to Python programs. Because at that point, you're parsing Python syntax. You have to deal with the idiosyncrasies of Python rather than the idiocies of PHP. And yeah, so at least the middle module you would have to completely substitute to make it work on Python, but there is no reason that it would, no fundamental reason that a similar system couldn't work on Python.
Except more engineering effort, but yeah.
Yes, absolutely.
That's fine. Cool, thank you. Are there any other questions from the audience? Let me ask one more about Saphire. What about fork and mmap? They are not in the dangerous system calls list. How do you handle those? And especially how do you handle fork? I'm more interested on that one.
So fork is not necessarily a problem because seccomp filters are inherited across fork. So even if as the attacker, you manage to fork the currently executing PHP process, the forked process, the child will still be limited to the exact same set of system calls. So yes, you can fork. Yes, you can potentially use that as a fork bomb and launch a denial of service attack. But the work is positioned against remote control execution vulnerabilities. So that's kind of out of scope for fork.
You already answered by inheriting syscall policies. That's fine.
Yep.
mmap?
mmap is a good question because mmap you pretty much need for all scripts because the interpreter itself will rely on mmap. So there's no significant limitations on that.
Right, because it brings up an interesting question where you would want to some extent to limit the parameters, not necessarily limit the system call, but parameters that are passed to specific system calls. Did you look into that?
Absolutely, we did look into restricting the parameters as well. But if you look at the performance evaluation, the reason we get the performance numbers that we get is because we only look at the system call numbers. These can be filtered relatively quickly.
Right.
You can filter on the arguments as well, but then you basically have to do 2 context switches into ptrace, have another application that inspects the arguments and then make a determination whether it should be allowed or not. Can be done potentially to more stringent benefit, but the performance numbers will very likely look significantly different.
Yep. Agree. Sounds good. Cool. Thank you very much. Last chance for questions, anyone? So Manuel is around for the next couple of months. We do have coffee, so shoot him an email and meet up for a coffee or a drink or a discussion or whatnot. And yeah, keep those questions coming. Thanks a lot for the presentation.
Thanks for hosting
it. And yeah, see you folks around. Thank you, folks.
Bye, guys.